And our way into chapter 2. Chapter 1, if you look at the ebook, the textbook for the chapter 1, a lot of reviewing about what functions are. Not completely, it's largely review. Some of the function ideas, if we need to, we'll review them right when we need. So 2.2. Last time, let's remember that. It seems like it's been a while since we off. Friday, we looked at two problems. We looked at the problem of trying to find tangent line to a curve. We looked at the problem of trying to find instantaneous velocity. And we saw that they both kind of gave us, we ran into this idea, taking limit. So we said we could limit, get our 2 points of our secant line closer and closer together. That there would be the slope of our tangent line. Turned out really the same thing applied with velocity. Time points and got those closer and closer together, we can start instantaneous velocity. So we're going to look at this limit idea a little bit more closely. In this particular, we're going to look at a few functions and talk about limit those functions to certain x values. So we're going to focus on doing this using graphs and using tables of values. And we'll talk about finding these limits more analytically next. So let's look at a function. Got function f, x squared minus x plus 2. We're going to pay attention to the values where x is close to x values around our table of values we're going to look at. So what we want to do is we want to get close to, we want to look at what happens to f of x, what happens to our y values function. So all we're doing, we're plugging in all these x values. I'm not going to make us go through every one of these. Because it's kind of tedious there, but if we plug in 1, that function we saw will get an f of x or a y value out of 2. And then the idea is we're trying to get close to x value of 2. We want to see what happens with our y value. We kind of experienced this already when we looked at moving our secant line points closer and closer together on the curve, how we could find the pattern and figure out where they were headed and what the value would be if we were actually able to get to 2. So here, coming in from what we would call the left side of 2, right, we're taking values smaller than 2 and getting closer and closer to 2. What's it look like is happening to our f of x values? Well, yeah, it looks like it's getting really close to 4. Really close to 4. So at 3997, 3985, 3997, and it looks like it's getting closer and closer to 4. So the same idea is happening with the other table. This time what we're doing is we're approaching x value of 2 from the other side, from the right side, where our x values are bigger than 2. So if we start off with an x value of 3, we get f of x of 8, and we are plugging in smaller values closer and closer to 2. And if we go down our table, our x values get closer to 2 on this side, then what's it look like is happening to our f of x values? Where does it look like they're headed? 4. 4. And if we think about the graph, look at the graph, that's not really surprising. Not really surprising. So what we're saying, when we say we're coming in from the left, we're taking these x values on the left side of 2, plugging those in to see what we get f of x. So as the x values we choose get closer and closer to 2, the y values that we get out of here, so when we get really close to, our y values are getting really close to 4. Close to f of x. If we come in from the other side, so we're looking at the right side, we evaluate our function at those x values, getting closer and closer to 2 from that side. And here we'll get this y value, and then this y value, and this y value, and we're getting closer and closer to 4 again, approaching that same y value. And I said this one's not surprising. Here's our function. Not too surprising, because what happens if we actually what are we going to get there if we actually do for our x? Yeah, we get so -2 plus 2 cancels out. We get 2 squared, which is so no shocker there. Not like life-changing. But we want to get used to the idea of our x values approaching some number without having to rely on actually being able to evaluate the function at that. So we could see from our table of values and from looking at the graph that as our x values get close to 2, our y values, the points on the graph, getting close to a y value. So we have a way to talk about that. That as our x values get close to 2, our f of x or our y values are getting close to 4. Say it like this, we call that a limit. The limit of our function f of x as our x values approach 2, 4, or shorter way of doing that is with this notation. This says the same. So we've got LIM for limit. Some people print that. Typically, when I'm handwriting, I do the LIM in cursive. You can do either one. When I'm handwriting, I do limit as the way we would read this. We've got a little x with an arrow pointing to 2. The way we would read that part is as the limit as x approaches 2, as x values get close to 2, of, we want to know what function we're looking at. So our function equals 4. This is saying with this function, as our x values get close to 2, our y value, our f of x value, are approaching. Some notation. Nice thing about this, where going to be most powerful, is we don't care if we have a function where we can actually evaluate it. That's irrelevant. Finding a limit here. So like we saw, we could pick up on the pattern and figure out what our limit was going to be without actually having to evaluate our. So that's one example. Let's kind of get a informal definition here, and what calls it the intuitive definition. So notation here, if we just read off the notation before we're looking at it, is the limit of some function f of x as our x values approach a, here a is just representing some number, that limit equals, and L would typically be some. So intuitively, what this is saying is that if we can get as close as we want to L on our y values by choosing values that are really close to our a values, say that's the. If we think back on our graph, can we get as close to the y value we want by changing our x value, moving it closer to some certain number at limiting? We kind of already talked about that. Not a lot there. Another way you can see limits expressed. So there's the one we've been talking about, the limit of f of x as x approaches a. Sometimes you'll see the same idea expressed this second way. It says our f of x values approach L as our x values approach A. Saying the same thing. Notation is not quite as compact and making it super clear we're talking about a limit there. That notation sometimes as well. So let me back up just a little. Skipped over one. So if we're trying to get close to this limit of L by making our x values close to this number A, thing that we're not concerned with, thing that's not required, that our x value is not going to be equal to A. Here we got it again. We're saying that as we approach our A value, both sides, our y values are approaching L. X value is not allowed to be A. So let's take a look. I'm beating around the bush. So let's look at some graphs here. We've got an A value. Okay, so this is what we're going to think about our x values approaching. Come in from the left and around to that A value. Draw on the screen. And from the left, right, for that A value with our x value. And we're looking at what's happening on our graph. So if we come in from this way, you can kind of see we're getting close to that y value. And if we come in from the other way, close to this y value. That's what we're calling L, our limit. This graph is one like we started out with. In this particular instance, let me get my scribbles off. In this particular instance, it's also true that if we just found f of A, we would happen to get that L value out of our function. That is not required. Not required. Because the limit's the same on these other two graphs as well. So if we look at B here, as our x values get close to A, either side, our y values still getting close to that y value L. So we're still getting close to this y value. But in this case, if we actually evaluated our function at A, we would not get L, we would get whatever this number is at that point then. And a similar idea on C, if we actually evaluated our function at A on that one, well, we can't even do that. We just got a hole in our graph there. Really, this function is undefined at x equals, but we could still find the limit. Is that making a little bit of sense? It's especially hard to read faces with people. So the limit's the same in all three of these. Now we've got three different situations about how the point x equals a is defined. Let's look at one with numbers. This one's telling us to guess the value of this limit. We've got the limit as x approaches 1 of our function. This time our function is x minus 1 over x squared minus 1. But if we look at this thing, if we tried to substitute in 1 for x, what's the problem? We tried x equals 1. We tried to find f of 1. What goes wrong on that? Yeah, it's undefined because we try to plug in 1. The denominator will get 1 squared is 1. 1 minus 1 is 0. So our function is undefined at x equals 1. We can't evaluate our function at x equals 1. But as far as finding the limit, that doesn't really matter because we're not looking at x values at 1. We're just looking at x values really close to 1. And how close to 1? Well, close as we want. As long as we're not actually at 1. So one way we could guess this limit is we could make a table of values. How could we check out our pattern doing the table of values? So we want to look at what happens on both sides of 1. So we would need some numbers that are smaller than 1, but they're getting close to 1. We would need some numbers bigger than 1 that are getting. We could plug those values in for x. What happens? F of x. So if we here's some numbers smaller than 1, but they're getting close to 1, right? So our book starts at 0.5 and then 0.9, 0.99, 0.9, 9. So as our x values get closer to 1 from the left side, what's it look like our f of x values are getting close to? Yeah, 0.5, 0.5. It appears, and then if we go on the other side of 1, so we're going to use numbers bigger than 1, but there we want to see how they trend as we get closer to 1. 1.5, 1.1, 0.1, 1.01. What's it look like it's happening to our f of x values in? Getting close to, I think, I know it's the same on both. Getting close to 0.5 on both. So, since that's the case, we could suppose, make our guess, what the textbook calls it, that the limit as x approaches 1 of this function is 0.5. We could come up with a similar argument. We're thinking about the graph. Here's part of the graph of this function, the part that we care about, the part close to 1. So first of all, on the graph, we said if we try x equals 1, function's undefined. So right at x equals 1, got a hole in the graph there, it's undefined. We can see as we pick x values on the left side of 1 and get closer to 1, our y values are getting closer to. Come in taking x values on the right side of 1 as we get closer to 1, our y values are getting close to. What's going on? I don't want to beat it to death, but I also want you to have a good idea of what's going on when we talk about it. Okay, slightly different function here. Got a piecewise function. The only difference is that we said this function is undefined at x equals 1, so now we're just defining it at x equals 1. Say the y values, in case the g of x values. So the only difference there is that if we actually plug in 1, function values at 2, but does that change the limit? No, because we don't actually care about what happens exactly at x equals 1 for our limit. We want to know what's happening close to 1 on. That's exactly the same as the. So our limit here, we could still guess would be x approaches 1. The idea from looking at a graph, you see where the graph's getting close to, and then if you have a table of values, you can kind of track the pattern and see. Like I said, we'll be much more analytic about it next section. We're just kind of trying to build our intuition about what's going on. So those are just right now what we're just calling limits. But think about a function like this. Got a little bit in your notation. We got this function h of t. Piecewise, but it's pretty simple. It says if our t value that we're using is less than 0, our h of t value is going to be. And if our t value we're using is greater than or equal to 0, h of t value again is going to be 1. So any negative t, we get 0. T is 0 or bigger, we get 1. So the thing we want to think about with this thing is that we get different values that we're approaching. Our t values are coming in from the left side. They're coming in from the right side. So this thing on the bottom, I tried to make them as big as I could. This one, the one I'm looking at. That notation's almost the same as what we've seen already, but we've got one little difference, and it may be hard to see if you're in the back, but on the 0, we have like in the exponent spot, superscript spot, we have a minus sign. Okay, so what that minus sign says is that we're approaching from the left side. So our t values we're using to get close to 0 are on the left side of 0, smaller than 0. So how do we know that limit's going to be 0? Well, if we're on the left side of 0, all those t values, that's going to be the negative t. So we're always going to get 0. And a little bit different on the other one. You can probably guess what this one is since we talked about the last one. But here this says we want the limit as our t values approach 0, and then we've got a plus sign up there. That means we're going to approach 0 from the right side. We're going to be using values that are bigger than 0. So in that case, we any t that's bigger than 0. Here's our notation. T approaches 0 from the left. Only thinking about values of t that are less than 0 or on the left side of 0. Have that second notation where t is approaching 0 from the right with the plus sign. We're only thinking about t values that are on the right side or that are greater than 0. Here we're only thinking about approaching our t value or our x value in general, one side. So we're going to call these one-sided limits. Here's our definition slide. It's really not much different. So here, if we read our notation, it says the limit of f of x as x approaches a from the left, because minus L. The only difference there is that our, from what the definition we've already seen, is that our x values have to be less than that, have to be on the left. Similar idea if you're coming to the other side. So when do we use these? So here we got part of a graph, right? Stops at A. So in this case, we couldn't approach A from the right even if we wanted to, because over here, any x value we pick not defined over there. Well, we've got some graph on the left, the domain, so we can just pick x values that approach x from the left, figure out our one-sided limit. And similar idea coming from the other side. This graph only starts at A, so we don't have anything on the left side we could use. So our x values just approach A from the right side. Any hanging in there? No, it's not super. Kind of have a decent grasp on notation. The ideas right now are not hard. Maybe if you're not familiar with a notation, okay, let's tie the two ideas together. You have what we just called limits to start with, and idea of these one-sided limits. So we saw before that if we took x values on one side of the value we were approaching, x values on the other side of the value we were approaching, we said we had to be approaching the same y value or the same f of x value. So this is just formalizing that idea. This says that the limit of f of x as x approaches a equals L. You can call that a two-sided limit. Thinking about approaching from both sides. The only way that can happen, if and only if, that limit equals L if and only if the limit from the left side of A and the limit from the right side of A both equal. So one way you can put this in more plain English, you can say the two-sided limit only exists if both one-sided limits exist, they're the same number. Look at the graph. Maybe this will be a little more. These, some of the little plus and minuses are tiny. I'll try to point out, those of you in the back, what we've got going on. So we want to find the limits by looking at the graph. And these are like what the homework problems are. So the first one, looking at this one, A, says we want the limit as x approaches 2 and it's 2 from the left. So where are we looking at on our graph? So we want our x values to be approaching 2. So on the graph, we're in this area for our g of x values or our functional values. What's it look like? As our x values get close to 2 from the left side, what's it look like is happening to our y values? They're getting close to 3. So our limit would be. B, want the limit of g of x as x approaches 2 from the right side, plus sign. So our x values, we're coming in from this side. So with our y values, we're following the graph. We're getting close to, we're getting close to a y value of 1. Our limit from the right side, approach 2 from the right, 1. C, it's okay. C, all it says is the limit as x approaches 2. It doesn't have a plus or a minus. So what does that mean? Which side do we care about if it doesn't have plus or minus? Both. We care about both. And yes. So we said as we come in from the left side, our limit is 3. As we come in from the right side, our limit is 1. So what's our limit as we come in from both sides? It says take the values, what? If they exist. What's the only way the two-sided limit can exist? That's back to here. That says if the left-sided limit and the right-sided limit both exist and they match, two-sided limit's that number. Here they're different numbers, right? Yeah, so we'll come in from the left, we're approaching 3. We'll come in from the right, we're approaching 1. Here we could say this limit does not exist, or shorthand. And that's what WebAssign, if you have one that does not exist, that's have one that doesn't exist, WebAssign will just get you put in. All right, let's look at D. So here we're approaching 5 from the left, their x values. So what y values it look like we're getting close to? 2, yeah. Oddly, that didn't, I guess, because the graph was there. So we're approaching 2. We come in from the other side. What y value does it look like we're approaching? 2. So the limit, just as we approach 5 with no plus or minus from both sides, what's our limit there? 2. So that's how they can work out. If you've got a two-sided limit, some value, and that only happens when the one-sided limits are both set. And if we have the case where the one-sided limits don't agree, two-sided limit does. Questions? Are you hanging in there? How's your semester going so far? Is it off rough start, easy start, rough, not so bad, got a mix? A lot of fun? Well, that's good. I know I was probably sarcastic. All right, so one more big idea. One more big idea. And that is the idea of having infinite limits. So what is this? Third day of calculus, and we're already having to deal with infinity. Doesn't take long. So infinite limits. So we've already got a lot of the notation out of the way, so we can kind of get over some of that. Got a function f, signed on both sides of a, then here we say infinite limit, we can write it down like this. F of x as x approaches a equals infinity. So what that means, little bit subtle here, but infinity is not a number. Infinity is a concept. So saying that something equals infinity, straight up saying that's a little strange. So we've got our interpretation of what we're really saying. That we're saying that our y values, our f of x values, can be made as large as we want, okay, arbitrarily large. We pick x values, or x values close enough to a. So what that's saying is that as our x values get close to a, our y values just keep getting bigger and bigger and bigger and bigger. The closer we get to a, the bigger our y value. That's what we mean by having a limit of infinity. And then we've got the alternate notation there. That is before f of x approaches infinity. Slide making the point infinity is not a number. So kind of has some alternate readings in the notation here. It says the limit of f of x as x approaches a is infinity. And instead of saying equals infinity, f of x becomes infinite as x approaches a. F of x increases without bound as x approaches a. Those all mean the same idea there. Just no, we're not saying that the function actually equals value infinity. A little more of a concept instead of a number when we have infinity involved. So what's that look like on a graph? We have an infinite limit on a graph. You've seen them before, you just may not have thought. So here's one. Here's our line x equals a. So if we come in from the left side following our graph, we don't have an arrow on there to indicate, but yes, it's gonna keep going up. We come in from the right side following our graph, keep going up, and the closer we get to a, the larger our f of x values are. We can make our f of x values as large as we want to just by picking close to a. So that line x equals a, we've got a name for that, algebra. We got a line where and it's a vertical line, so that gives us part of the name. Vertical line, and our graph gets closer and closer and closer to that line, but it never actually touches it. Vertical asymptote, yeah. So here, x equals a, vertical asymptote. Vertical asymptote. So if we have infinite limit, f of x approaches infinity, then we have a vertical asymptote. We can do the same idea for negative infinity. Our graph's going down, if our f of x values are getting, you could say, smaller and smaller and smaller, or we're going to have some terminology that we use sometimes to try to be extra clear about what we're meaning by small. Got this terminology here, large negative. That means a large magnitude number but with a negative sign. Really, really far down on the y-axis. What we would call a large negative. So Their x values approach a, our y values become large but negative as we want them to be. Both directions. Limit negative. So same idea on the definition of nothing going on there. We've got an example. That one. Okay. So these are two-sided and have the same idea. One-sided limits. We could work a definition, just use ideas we did others. We could have a situation where we say the limit as x approaches a from the left is infinity, right's infinite, or we could have negative. Same idea. The minus sign means we're coming in from the x values on the left side. Plus sign means we're coming in. Not so much. So let's look at the picture. So this is really tiny, I know. So this is saying the limit of f of x as x approaches a from the left, infinite limit. As we come in from the left side, it goes up without bound. And the limit as x approaches a from the right, goes up without bound, is infinite. When x approaches a from the left side, so a with the minus sign, down without bound. And as we approach a from the right side this time, it goes down without bound. Limit is got those? Idea what they look like? Think so? So we've already mentioned it, but if any of the following statements are true, that means the line x equals a is a vertical asymptote. So this slide comes in really handy when you have a problem that says find the vertical asymptote. So if any of these are true, so if the two-sided, left-sided, or right-sided limit approach a, infinity or negative infinity, I call the line x equals a vertical asymptote. We've seen graphically, geometrically, what you think that is a vertical asymptote. There. Let's look at an example. So these slides are, somebody asked last time if I would put the slides up, and I forgot until I saw that I forgot today. So I got the slides from last class and don't count. And I'll try to post them before class. If we use slides, we might not use. Get this. It says find the vertical asymptotes if f of x equals tangent x. Oh, we got trig in there. Not too bad. So tangent we can rewrite as sine over cosine. And that's maybe a little bit easier to think about. So thinking anywhere where our denominator is 0 is potential vertical asymptote. So then let's track along with the rest of this fact. Cosine of x approaches 0 from the right side as x approaches pi over 2 from the left side. That's a little, we can get some practice in thinking about the notation, right? This says as we We use x values that are smaller than pi over 2, close to pi over 2. And our cosine values are going to get close to 0, but from which side? From the right. So they're going to be positive or negative. If we're coming into 0, if we're getting close to 0 from the right there, it'll be positive. Positive. So it's saying we get positive cosine values, have x values left side of pi. Then we've got negative cosine values for coming at pi over 2 from the right side. And that's thinking about what happens on the bottom. On the top, sine x is going to be positive, and x is near pi over 2. So what happens? We take those two signs together. So we're coming at pi over 2 from the left side. That gives us positive cosine, and sine's also going to be positive. We're going to be approaching positive infinity. We're coming in from pi over 2 from the right side. Cosine values are going to be negative while sine is positive, so we'll have a positive over a negative down to negative. And here's a picture. 3 interval there. Multiple of pi. Okay, we're looking at pi over 2, but then we can also add multiples of pi to the left side. We're going down, right side. Pretty uncomfortable with trig. Trig's not my favorite. We won't be real. Okay, so that said, let me give you two little examples here that may be more interesting to you. Let's think about a couple of functions here. I will call these Cronquist. Call these functions cautionary tales. So what we said we can, in this section, we can guess or we can estimate the limit of a function in a couple of ways. We can look at the graph, and we can say, well, as our x values are going these directions, our y values getting close to a certain number, so our limit. Or we've said we could use a table of values, and we just see what the pattern's doing in our table of values as we get close to a certain x value. Let me give you a couple where that's not as straightforward as it seems. So let's think about this thing. Limit as x approaches 0, sine of and here taking x values, plugging them in trig function. You're going to want to be in radians. If we ever do anything in degrees, it'll be specified. Okay. So let's think about some values. So we want to get close to 0. we'll make it easy. We'll really just, since we're doing it together, we'll just do from the right side. We'll just do a positive. Trying to get close to 0. So what do we want to do? We want to 1 maybe. Trying to make our x value smaller. So if you want to try it in the calculator, make sure you're in radian. So we want sine of pi over 0.1. Or another way you could put that in, pi divided by 0.1 and pi. You could put it in either way. Divided by. Can I try it? The way I typed it in, I just typed it in. Pi divided by 0. Sine of pi divided by. You should get, if you're in radians, you should get. Ooh. If you leave that on your screen, then it makes it easier. You can just go insert the other 0. So do pi divided by 0.01. Pi divided by 0.001. Yeah, good guess. Would you try it? Yeah, we do get 0. So what's your guess on the limit? I said yes, so it's okay. What's it look like? As our x values are getting smaller, our function values, sine of pi over x, are what's our pattern? Zero. Yeah, let's look. They're all the ones we tried are 0. So you get the same thing for all of them, then that's, you don't have to tell what you're approaching, right? You're actually at something. So this, to me, just looking at this table, that seems like a very strong indicator that as our x values approach 0, or the limit of our function would approach 0. That's very wrong. That's very wrong. Let's look at the graph. We want the graph of sine over pi x. Just saying to be careful. Okay? It's just cautionary tales, right? Be careful. You can deceive yourself if you're. Want sine of pi over x. We want to look at x values close to 0. What's going on there? Maybe we need to zoom in a little bit. Zoom in. What's happening? Tell me, zoom in a little bit. What's happening on the graph? We got a name for this kind of behavior. What's happening is, as we're coming from both sides, graph is bouncing back and forth between the value. That's the y value 1 up there. This is the y value -1 down here. Graph is bouncing back and forth between those, and as you get closer and closer to 0, it bounces faster and faster. Know what that behavior is called? Have an oscillation. We're oscillating between 0 and 1. just so happened that at the x values we picked, which those are common to use if you're trying to get close to 0, you divide by 10, your x value by 10. So happened that the x values we picked were places where the oscillation crossed the x-axis. But if you look at the graph, we don't have a nice limit approaching 0. We've got this infinite oscillation back and forth. So there are infinitely many x values you could plug in and get 0. Also infinitely many x values you could plug in, get 1, negative 1 or 1. And the infinite oscillation back and forth there. So in this case, we don't even have a limit. This is one way we did not have a limit. We don't even have a one-sided limit because of this infinite oscillation. And if you plug this thing into a graphing calculator, your mileage may vary on what kind of graph you get. Sometimes you don't get a very nice picture there close to 0. Hard to tell. So be a little careful. That's one reason why we talk about two methods of estimating these things. So one's looking at a table of values, so checking out what's going on with the graph. It's a good habit to do both. Because if we had just relied on our table of values on this one, it would be very wrong. Our limit is very much not 0. All right, so one other cautionary. Limit, x approaches 0. T on this squared plus 9. Okay. So we could do the same thing. We could, well, the t's this time. T, and then I'm just going to call it f of t. So we're just thinking about plugging in some values here. In this case, it turns out like whatever t value we plug in, both places it's getting squared. So we're going to get the same thing if we plug in the negative version or the positive version. So it cuts our table making in half. Like we can plug in plus or minus. So trying to get close to 0 again. So maybe plus or minus 0.1, plus or minus 0.01. 0.01. So these, they're worth trying in your own calculator, even if you don't have it today. Particular ones worth trying just so you figure out the limitations of your calculator. So I'm going to do 0.1. So that'll be the square root of 0.1 squared plus 9. That's all under the radical. Minus 3. We want to divide that by 0.1. So on mine, I get 0.1 something. I'll do the next row, so I'm going to do 0.01. One, 6, 6, 6, 0 something. Do one more. 0, 0, 1. my calculator. I may have one that has a bit better memory than mine. I get 0.1, 6, 6, 6, 6, 9 in, so it's not saying it's repeating anymore. It's saying that that's my first issue. So what's it look like our limit is getting close to? This one's not a trick. What? Yeah, 0.16 repeating. So it appears that our limit approaches 0 of that thing. I'm gonna call it f of t. Is 0.16 repeating, which has a fraction. Anybody know what 0.16 repeating as a fraction is? Yeah, 167 here. And so as a fraction, it's, and that is in fact the limit of this. Haven't quite run on my calculator. We haven't quite run into the problem yet. So on yours, if you want to know how good your calculator is, so I'm gonna skip a row and I'm gonna do one more because I know mine messes up on this one. 4 zeros. So we're gonna try and get really close to 0, right? So we can get a really good idea of where our pattern headed. So I know mine will not. I tested mine earlier. Mine will not do correctly. Oh no, it actually did. I gotta have one more on mine. My little cheap calculator is pretty good here. I need 5. Everyone's calculator at some point will run into this issue. It's just how many zeros you can, how small you can make your values. So on my calculator, if I put in 0.0000001 t, my calculator says can't keep up. Too small. So on 4 zeros, mine said this. I'm losing information. And 5 zeros. So the issue there, if you put in values close enough to the value you're approaching, so here we're close enough to 0, eventually the numbers get too small for the calculator to handle correctly. And it'll say, oh, that's so small, it's 0. Our limit on this is not 0. If we try to be too precise, not 0, our limit is. And we can verify that with a graph real quick. And let's square root of, I'm gonna call it x. X squared plus 9 minus 3. All that was over x squared. Here's our graph. Nothing crazy going on there. Goes through the y-axis right at 1/6. Not at 0. Be a little careful. Okay, technology can be a good tool. Calculus may be the first place your calculator's letting you down as a student. But at this point, you may not feel like it, but at this point, at least by the time I get done, you're smarter than. You're gonna have to keep an eye on your calculator because it can't keep up with you. Right? Questions on those? Alrighty, well that's it. We'll stop there and talk about doing